Really nice.
Yeah. Great, thank you, everyone. Today's speaker is Bryan VanDuinen. He's a professional engineer with more than 13 years of experience investigating and remediating contaminated sites, with a particular expertise in vapor intrusion and chlorinated solvent impacts. Based in Geosyntec's Michigan offices, he serves as one of Geosyntec's vapor intrusion technical leads. It's helped advance innovative assessment tools such as building pressure control, high volume sampling, and passive gas methods to quickly characterize vapor intrusion risk and design mitigation systems. Bryan has contributed to state and federal cleanups, developed the Michigan Department of Environment, Great Lakes and Energy's vapor intrusion sampling procedures, and has supported guidance updates. Today's seminar highlights the challenges of evaluating vapor intrusion, including background sources, spatial and temporal variability, preferential pathways, while demonstrating how new tools and case studies can improve understanding of vapor intrusion in real world settings. Please welcome and join me to welcome Bryan.
Thanks, everyone. So thanks for the introduction, Brendan. I'm here to talk about a subject that's near and dear to my heart, vapor intrusion. Start with the basics, just sort of make sure we have a kind of baseline understanding. I'm not expecting everybody to necessarily know everything about vapor intrusion right now. Talk about the challenges that we can face with vapor intrusion assessment, and then talk through some of those sort of innovative technical solutions that we've developed to try to address those challenges. Hopefully have time for a case study at the end. And throughout this, I'll be kind of talking about this through the lens of an attenuation factor, and I'll explain what that is and different ways to think about it. So vapor intrusion. Vapor intrusion is when you have a contaminant in the subsurface, in the soil or groundwater, or as a free phase liquid that can volatilize, essentially evaporate, enter the vapor phase, move out of the vapor through the soil and get into overlying buildings and cause an indoor air quality issue. How do we go about investigating this? Well, this is the flow chart from the Michigan Department of Environment, Great Lakes and Energy. They're in the middle of updating their VI guidance, but this is kind of the same general approach that you find in most guidance documents. You would start by defining the extent of the vapor source. So where do you have contaminated soil and groundwater that could cause a vapor intrusion issue? You apply a lateral screening distance out from that source. That determines your investigation area, and then you're going into buildings within that investigation area to assess those, and if necessary, to mitigate those if vapor intrusion is happening. So how we go about doing that? I mean, first we would start typically with soil and groundwater sampling, kind of understand the extent of the vapor source, and then we would apply a certain step out distance to define a lateral inclusion zone. So we have this sort of hypothetical building here where there's been a release, and there's this lateral inclusion zone, so we need to look at vapor intrusion at all of these buildings, not just the site building, but some of these residences that are just off-site in this hypothetical scenario. What this inclusion zone, this distance is, depends on whether your contaminant is petroleum or not petroleum. Typically, when we're thinking of not petroleum, it's more chlorinated solvents, things like trichloroethene, tetrachloroethene, perchloroethene, which is sort of the old style dry cleaning solvent. Petroleum hydrocarbons readily break down in the presence of oxygen, which means they don't travel as far, either dissolved in groundwater or as vapor. So that means that that lateral screening distance is only going to be about 30 feet for petroleum hydrocarbons compared to 100 feet for non-petroleum contaminants. It also means that there's a vertical separation distance for petroleum. So, you know, you have oxygen sort of coming down from the atmosphere from the surface. You have your vapor source sort of vapors coming up from the source in the subsurface. And then where they meet, there's this sort of interface where aerobic biodegradation happens. So as long as you're getting oxygen to the subsurface and you have a sort of minimum separation distance, which is 5 feet or 15 feet, depending on whether your source is groundwater or whether you have that free phase liquid, which we would call LNAPL in our jargon. That's going to be sufficient for that degradation to happen and for you not to have vapor intrusion concern for petroleum. No such luck for your chlorinated solvents. Okay, so we've established, here's our vapor source, here's our lateral inclusion zone, here's the area we want to investigate for vapor intrusion. How do we actually then go and investigate vapor intrusion in a particular building? So conventionally, we would drill through the bottom floor slab of the building, install a sub-slab probe, a vapor pin, and then we would collect samples of sub-slab soil gas and indoor air using these evacuated metal canisters, 1 liter or 6 liter, 1 liter for soil gas, 6 liters for indoor air. Indoor air is typically over like an 8 to 24-hour period, depending on whether it's a residential or commercial industrial building. And then we're taking those samples, sending them off to the lab and getting, comparing those concentrations to our established screening levels. So if we have soil gas concentrations and indoor air concentrations above a screening level, that's a pretty good indication that vapor intrusion is happening at this building. So then what we would do about it, we typically put in a mitigation system that, if you're familiar with like a radon mitigation system, would look a lot like that. So we would either core through this bottom floor slab, sort of dig out an extraction sump, connect piping from that sump to a fan outside the building that then vents above the roof of that building. So we're basically sucking up the vapors from beneath the slab, venting them above the building, preventing them from getting into the building in the first place. If there's a sump, you can perhaps just attach to that, put a lid on that, and extract directly from the sump. An attenuation factor. So attenuation factor is simply the ratio of an indoor air concentration and a subsurface concentration. It could be that sub-slab soil gas, it could be deeper soil gas, groundwater soil. I'm going to keep it simple and just talk about sub-slab soil gas for the duration of this presentation. One thing to keep in mind, which is maybe a little counterintuitive, is that the higher that attenuation factor number is, the more that vapor is getting in, right? The higher that indoor air concentration is relative to sub-slab, so it's actually less attenuation that you're getting. We can think of this attenuation factor in 2 directions. So kind of the forward direction is, if I know the attenuation factor of a building, or if I assume an attenuation factor of the building and I know a sub-slab concentration, then I can calculate what I would expect the indoor air concentration to be in the building. It can also go the other way, and this is what a lot of regulatory agencies do, is they have an indoor air screening level or an acceptable air concentration. They have an assumed attenuation factor, and they can use that to calculate screening levels for the subsurface media, for soil gas, for instance. Now, EPA did this empirical study where they pulled in pairs of sample data from a handful of sites. I think they had 500 different pairs of indoor air and soil gas data, and they just calculated the attenuation factor and sort of did evaluation statistics on that. So this is kind of the big takeaway of their evaluation. I guess the median attenuation factor is about 0.003. So if you have 1 microgram per cubic meter in the subsurface, you would expect 0.003 micrograms per cubic meter in indoor air. But there's a huge range on this, right? So that's the median. The 95th percentile is 10 times less attenuation. The 5th percentile is 10 times more attenuation. So that's a pretty decent spread. A lot of regulatory agencies, including the Michigan Department of Environment, Great Lakes and Energy, have taken that 95th percentile and used 0.03 as their default, their generic attenuation factor, and use that to calculate a generic subslab screening level. I think that's a reasonable approach. That's conservative. That would be protective of 95% of buildings based on this study. I think the one danger is when that screening level becomes an action level. So you go out, you collect samples, your subslab soil gas concentrations are above this screening level, and then you immediately jump to, oh, well, now we need to mitigate that building. The problem is this is the 95th percentile, right? So 95% of buildings would have more attenuation than what you're assuming based on that. There's some other critiques that have been applied to the study. I guess the first is that most of these data were from residences with basements. So if you're looking at like a commercial industrial building, you would expect more attenuation to happen. You would think that that bottom floor slab is probably thicker and more competent than what you would see in a typical residential basement. You might not see a basement in a commercial industrial building, so you have more separation from the source. You would also have kind of better air circulation in the building. You're bringing in more outdoor air, you're diluting whatever is intruding from beneath the building. On the flip side, if you had a residence with like a dirt floor crawl space or our Michigan basements that don't have a floor slab, you might expect less attenuation to happen. Another criticism too is that most of these data were collected from sort of cooler parts of the United States. So most, like over 50% of the data were from 3 sites, which were in New York, Connecticut, and Colorado. We would generally expect that cooler climates and when the building is being heated would be worst case for vapor intrusion. We'll get into that later. So you can imagine that like Southern California, you might expect better attenuation than what's coming from this national study. Okay, so I've started to hint at some of our challenges. The thing to keep in mind is that this is very complex. There are lots of different things that play into what is in indoor air in a building at any given moment. So there's probably the more obvious things from the environmental perspective, like what are the concentrations in the soil and groundwater? What is the soil type? How easily can vapors move through that soil? How wet is that soil in that moment? Because the more of those pore spaces in between the soil grains are filled with water, the less able the vapor is to move through that. But then you also have things going on at the surface. So how is that building constructed? What is the weather like that day? What kind of heating and cooling system does that building have, and how is it operating? And are there other things just from sort of commercially available products in that building that might be off-gassing and contributing to indoor air beyond what's coming from vapor intrusion? So that makes it all very technically complex, makes my job more interesting. So background sources, on this left side, I have a graph looking from a study looking at how often are these contaminants found in indoor air in a building when there's no subsurface vapor source. So you can see that a lot of our petroleum compounds, toluene, xylene, benzene, ethylbenzene, those are present at more than half of our buildings. Also seeing methylene chloride, chloroform, tetrachloroethylene, tetrachloroethylene or PERC. Again, that's sort of old style dry cleaning solvent. So if you're getting your clothes dry cleaned and your dry cleaner uses that, see it in the indoor air. Chloroform is also a byproduct of drinking water disinfection, right? So municipal tap water will use chlorine to disinfect the water, get rid of the viruses and bacteria, but it will also react with organic material and can create chloroform. And then when you run a faucet inside your house, some of that chloroform will off-gas and end up in the indoor air. So not only do we see it, but we see it at environmentally relevant concentrations. So the numbers in those parentheses is kind of the range of the laboratory reporting limits. So sort of the minimum amount that's in there for the lab to detect it. And some of those reporting limits are above like what your indoor air screening level would be. So you could have an indoor air quality issue just from a background source And then when you have, vapor intrusion investigation, how do you distinguish between what's in the background and what's coming from vapor intrusion? So if you think about how that affects our attenuation factor, you can kind of split it up that the indoor air concentration is going to be a combination of a sort of background contribution and then what's coming in from vapor intrusion. So again, your subslab concentration times the sort of real attenuation factor alpha. So we have like this hypothetical scenario here where we have the indoor air concentration versus the subslab concentration where the background is 1 microgram per cubic meter and the real attenuation factor alpha is 0.001. So you can see that kind of that low subslab concentration is basically all of what's in the indoor air is from background, and then as we kind of increase what's in the subslab, then all of what's in the indoor air is coming from vapor intrusion. Now, if we were doing an empirical attenuation factor and just collecting an indoor air sample, collecting a subslab sample, taking the ratio of those two concentrations, if we divide this equation by our subslab concentration, then our apparent attenuation factor is going to be the sum of the real attenuation factor and then the ratio of the background contribution and the subslab concentration. So at these low subslab concentrations, the apparent attenuation factor looks much higher than the real attenuation factor because of that contribution from the background. It's only once you get up to these higher concentrations that the empirical attenuation factor is matching what the true attenuation factor is. So we did this analysis at one of our sites, a large commercial industrial building. We had multiple co-located samples, multiple sampling events between, and we're just plotting indoor air and subslab at multiple locations. And we can see that this generally follows that pattern. At low concentrations, we have a higher apparent attenuation factor, in the worst case, something like 0.0024. But when we do this analysis, we think our real attenuation factor is about an order of magnitude less. Another challenge is temporal variability, particularly in indoor air. So Arizona State actually bought a house to do research above a TCE plume and did a lot of sampling, a lot of different investigations there. One of the things they did was take a daily indoor air sample over an extended period of time. And this is a logarithmic scale on the left side here. So you can see that there's over 1,000 times factor of difference between our lowest indoor air concentration and our highest indoor air concentration. And when you're thinking about sort of long-term chronic exposure, those infrequent spikes are what's contributing to sort of most of the exposure, most of the contaminant mass that an inhabitant would be inhaling. So when do you collect those indoor air samples? How many do you need to collect? How do you collect it? If you collect an indoor air sample and your concentrations look low, they're below the screening level, is that because that building is not susceptible to vapor intrusion, or do you just catch it on a good day? And it would be a problem if you came back the next season or even the next day. Another variability problem we have is spatial variability, and this think about more in the subslab soil gas context. So here we have a large commercial industrial building, probably 100,000 square feet. And, the consultant that did this initial investigation is looking at that state's guidance document that says you need a subslab probe every 1,000 square feet, 2,500 square feet, whatever it is. The Swiss cheese is this floor slab with 100 different vapor pins. And you can see there's quite a range. I don't know if it's able to be made out here, but the highest concentration here is around 30,000 micrograms per cubic meter, and the next door pin is less than 1 microgram per cubic meter. So we have a huge variation in concentration, and hopefully there was some method to where these probes were placed, that they're kind of biased towards historical operations or known releases. But if you're looking at like the size of these hotspots and the gaps in between some of these vapor pins, you know, there's a chance that there's a whole hotspot that's missed here, even though they've put in, you know, 100 vapor pins to characterize this slab. So again, how many samples do you need? Where should they go? How many do you need to collect? How do you collect them? And then the last challenge is preferential pathways. So you can have like a sewer where you have contaminated groundwater that's entering into that sewer, or it might be going through contaminated soil and there's vapors going into that sewer. And then that can travel through sewers, other utilities, and then kind of directly get into buildings through that. So, you know, typically you want to have that sort of U-bend, that P-trap of a water gap so that you aren't getting sewer gases coming back into your house. But if you have like a floor drain that's dried out, if you have, you know, that one sink in the basement that nobody uses, then you might be getting these vapors coming in from this and just bypassing the subsoil gas entirely. All right, so if we think back to our conventional vapor intrusion assessment, we're collecting subsoil gas samples, we're collecting indoor air samples in these metal canisters. We're then taking those concentrations, we're comparing them to the screening levels. So we could have subsoil concentrations above or below our subsoil screening level, indoor air concentrations above or below our indoor air screening level. And we could get a black and white answer. We could have a situation where both media are less than their respective screening levels. That's a pretty good sign we don't have vapor intrusion happening. We want to come back just to make sure there isn't like a temporal variability effect. But this is a good indication that we don't have a vapor intrusion issue. On the flip side, if we have exceedances in both subslab and in indoor air, that's a pretty good sign that the vapor intrusion pathway is complete and that building warrants mitigation. But we could have a shades of gray answer. We could have a situation where subslab concentrations are above the subslab screening level, but indoor air concentrations are less than their screening level. So it might be that, you know, we don't have that 95th percentile building, we have a median building or a better building, and it's just has really good attenuation and is not susceptible to vapor intrusion. Or we could have just collected that indoor air sample on a really good day. And if we came back later, we would have an indoor air exceedance. We could also have the flip side where we don't have subslab exceedances, but we do have indoor air exceedances. And in that case, you know, did we just not put the subslab probe in the right place? There is a subslab soil gas source that we missed. Is there a preferential pathway that we missed where it's coming in through the sewer? Or is that indoor air concentration just a background source and has nothing to do with the site contamination? And, you know, these questions get to you know, really fundamental parts of the project. So if I'm a consultant that's representing a private property, a liable party that's trying to address their site contamination, and we get this scenario in the bottom, you know, whether or not that's a background source versus vapor intrusion depends. You know, that will affect who is responsible for addressing it. It shouldn't be my client's responsibility if there's just a canister of solvent underneath somebody's sink. It also means that if we go through the trouble of putting in a vapor mitigation system, it's not actually going to improve their air quality if it's a background source. So really thorny questions, and you could go out and just collect, you know, the same thing over and over again, do like 4 rounds of seasonal sampling, and maybe not really resolve the issue of what's going on. So some of the technical solutions that we've developed to try to address these challenges. There's a range of them. I'm going to focus on the ones that are highlighted in blue. So building pressure control, which will help address the challenges of background sources and temporal variability. High volume sampling, which gets to spatial variability. We can do pneumatic testing with that, which can assess preferential pathways. And then with, either the building pressure control or the pneumatic testing, we can come up with building specific attenuation factors and then building specific screening levels that are more reflective of what's going on at the site. All right, so one of the key factors influencing vapor intrusion is the differential pressure between the building and the gas beneath the floor of the building. So if that building is depressurized relative to the subslab, that's going to draw vapors in from underneath the building. If you turn it around, if the building is pressurized, that's going to kind of prevent vapors from coming in. There's a few things that can affect that. One is just wind. So you can create positive pressure on the windward side of the building and negative pressure on the leeward side of the building. You can also, like in the cooler months when the building is being heated, hot air rises, right? So that's going to create a stack effect that's going to induce a negative pressure at the bottom of the building. So between that and windows and doors being closed in the winter, that's why we think that generally cooler weather heating season is when vapor intrusion will be worse. So we can look at the differential pressure across that slab in a building over an extended period of time. We can get different sort of signatures from different buildings. Some will just sort of be neutral. There's no sort of net differential pressure. Some buildings can be pressurized relative to subslabs, some can be depressurized. Again, that would be more susceptible to vapor intrusion. And often we see this sort of cyclic sort of back and forth that, with the diurnal weather patterns, heating and cooling system turning on and off, that differential pressure is sort of switching between pressurized and depressurized over the course of the day. So instead of relying on whatever the natural differential pressure is, we can use building pressure control. So with that approach, we would start by monitoring the natural cross-slab differential pressure. That'll tell us whether the building is susceptible to vapor intrusion. We might be able to discern, under what conditions is the building pressurized. So then we can actually directly manipulate that differential pressure. So depressurize the building, essentially turn vapor intrusion up to 11, and get our worst case scenario. Then we can turn that around, pressurize the building, essentially turn off vapor intrusion, and then whatever we're seeing in indoor air is likely from a background source and not from vapor intrusion. So how do we do that? We use this blower door, which was originally developed for building efficiency, but we've adopted it for our own nefarious purposes here. We'll typically collect indoor air samples under 3 different scenarios. One is just baseline, where we're not manipulating the differential pressure. One is depressurization, so we have this fan in the blower door that's sucking air out of the building and inducing that negative pressure inside the building. And we can flip that fan around, pressurize the building, turn vapor intrusion off. Typically, for the depressurization, we're collecting our samples right at this fan because that's sort of, our spatially integrated sample where sort of anything that's coming into the building is coming out at that fan. For our pressurization, we'll do a wandering wanda where we just sort of take the sample and sort of carry it around the house to get that spatial integration. So here's some example data from a building that we did while we were developing this. So we'll just start with this sort of 0 Pascal line where we're not manipulating the differential pressure. You can see that our PCE concentration here is just below the screening level, so we may be worried that vapor intrusion is a problem at this building. But then in this case, we depressurize the building at sort of 3 different differential pressures. And even under the highest one, that indoor air concentration is still below the screening level. So we have some good assurance that even under worst case scenario, we don't have an indoor air exceedance. The building is safe. On the flip side, when we pressurize this house, we still get measurable PCE concentrations in the indoor air, about 5 micrograms per cubic meter, which tells us that there is a background source that's contributing to the indoor air. I mean, vapor intrusion is still obviously a problem here because there's a difference between pressurized and depressurized, but there is a contribution. The nice thing about this is you can do a BPC test in about half a day to a day. And typically your alternative is doing like 4 rounds of samples 3 months apart to evaluate the temporal variability. So now we're just sort of creating that worst case scenario instead of hoping we'll catch it 9 months down the line. So the advantages over conventional sampling, we're reducing spatial variability. We're getting that sample at the fan that's representative of the spatial average of the whole building. Also, by depressurizing the whole building, anywhere that vapors can come in, we're going to be drawing them in. So we're not worried about potentially missing something from a subside vapor pin that's not in the right spot. We're also reducing temporal variability. We're generating that worst case conditions. If you think back to the slide several slides ago where indoor air concentrations vary by over 1,000 times, when we do this repeatedly, we typically see about a 2 times variation with the building pressure control. The other nice thing is you're collecting those indoor air samples the same way that you'd be collecting a conventional indoor air sample. With Suma canisters for volatile organic compounds, maybe sorbent tubes. But it means that the sample collection and then the analysis and interpretation is basically the same as conventional sampling. All right, so back to the attenuation factor. For building pressure control, we can come up with an attenuation factor that's representative of what's going on in the building, but is still conservative. So by creating those worst case conditions, we can get a worst case indoor air concentration. We can put in an average representative subset concentration and come up with an attenuation factor for that building. The nice thing is, if you're in a location where radon is an issue, you can also measure radon subslab in indoor air and get another line of evidence for what the attenuation factor should be. Okay. The other technology that we have employed is high volume sampling. So this is kind of getting around the problem of spatial variability. So instead of collecting a conventional soil gas sample, which is about 1 liter from a specific point, what if we collected tens of thousands of liters and draw in from a wider area? So we have, a very sophisticated pump from the good people at Shopback, and a PVC pipe that we're installing through the slab, and we're pulling soil gas out from underneath the building, venting that safely outside, and collecting measurements as we go. So we're seeing how do VOC concentrations change, how do carbon dioxide, oxygen concentrations change over time, getting field measurements of that. And then we're also collecting our Suma canister samples for the full laboratory analysis. So, if we have this photoionization detector reading that's giving us a sense of the total volatile organic compound concentration, it started off kind of on the lower end during this HVS test and then pegged out the instrument at 10,000 ppm. So this is telling us that we may not exactly be on top of that source where our location is, but we have a pretty significant vapor source not too far away from that location. And if you think about a conventional soil gas sample, you'd have just gotten what was here and you would have missed what was here unless you had another vapor pin in that. We can also look at oxygen and CO2 concentrations over time. And this is a good indication of sort of the extent of leakage, how much indoor air is leaking through that floor slab or how much outdoor air is leaking kind of out from outside the building. But it gives us a good sense of how competent that floor slab is. So if we have low O2 concentrations, high CO2 concentrations, and they're maintained, that's a pretty competent floor slab. The other thing we can do is pneumatic testing. So we're pulling the soil gas out. We have this concrete slab. We have native soil or granular fill underneath it. We have soil gas that's sort of being drawn into that suction point through that soil. We have air that's leaking across that floor slab through cracks, utility penetrations, what have you. And it turns out this looks a lot like if you have an aquifer with a leaky aquicard on top of it. And we have a hydrogeologic model that describes how, water in that aquifer moves. We can just repurpose that for this scenario. It's still fluid flow through porous media. It's just, air instead of water and concrete instead of clay. There's two key parameters that come out of that. There's transmissivity, which is telling you how well that fluid is flowing through that granular fill beneath the slab, or the aquifer in the original case. And then you have a leakage factor, which I tend to think of as like an equivalent thickness of that concrete slab or that aquiclude. So again, you have another factor where we call leakage, but the higher that leakage number is, the more competent that confining layer is. So, we can do the equivalent of a pump test in hydrogeology with this high volume sampling approach. So we can have, we'll have our suction point in the floor, but then we can drill other holes at various distances away from that. We can get a sense of the static vacuum. How does vacuum change as a function of distance from our point? Then we can also cycle that shop vac on and off and get pump test data, look at that vacuum over time. And then we can use those data, use software available for aquifer characterization, get those transmissivity and leakage values, which we can then use to look at all kinds of different things about how the fluid is flowing through that subsurface. So we can look at vacuum as a function of distance, the velocity of that soil gas, the travel time, how much of that soil gas is from indoor air leaking across the floor slab. And if we need to mitigate this building, these are great data to have to use for the design of that mitigation system. The other thing that we can look at is we can come up again with a building-specific attenuation factor. So here, I've talked about it as like the ratio of indoor air to the subslab concentration. That's also equivalent to the rate that vapors are coming into the building versus the rate that fresh air is being circulated through the building. I'm not going to show how I derived this, but if you're interested, we can talk about it. But basically, we can use that transmissivity and leakage values, the T and B, from the pneumatic testing, and then three other variables. So one is the differential pressure across the floor slab, which we can measure, the height of the building, which we can measure, and the air exchange rate. So how quickly is that air volume within that building being replaced from fresh outdoor air. That's something that's a little trickier to measure. We can do it. If it's all coming in through an HVAC system, we can do like a test and balance of that heating and cooling system. There's tracer gas methods. We can also just assume a conservative value that's kind of out there from the literature. So again, we can calculate an attenuation factor using building-specific data and kind of come up with a better description of what's going on at this building instead of just using a generic value. Okay. So finally, okay, that's all very nice. How can you actually apply these tools? So sort of walk through a site in Michigan where we did high volume sampling and how we used that data. So before we jump to high volume sampling, we did do the conventional sub-slab indoor air sampling approach. We had historical information that suggested that the release was kind of in this this sort of Tetris block shaped courtyard in the middle of the building. So we we kind of started in the center and sort of marched sort of outward in four different directions from here. And these are the sub-slab numbers that I'm showing here. Cells that are highlighted in gray are where we have exceedances. So you can see that sort of towards the center of the building, we have concentrations as high as 89,000 micrograms per cubic meter. That tends to drop off as we move sort of farther from this source area. We collected co-located indoor air samples. And again, similar approach, and did 4 quarters of monitoring. And again, at the last seasonal sampling event at one location, we had an indoor air exceedance. So we had 15 micrograms per cubic meter that was above the screening level at the time of 8.8. It's also about that time that the state's telling us that, yeah, we're going to be revised in our screening levels. So that number that's sort of acceptable is going to go more from like 8.8 to something more like 2. So we have an area that like we know we need to mitigate, and it's just a question of how much of this building needs to be mitigated and how do we design a mitigation system. So we did I think 15 different high volume sampling locations throughout this building, locations towards the center where we've already done subsoil gas and indoor air sampling. We just kind of focused on the pneumatic properties and did the full HVS test where we're looking at CO2, O2, VOC concentrations around there. So, to establish where do we need to mitigate, and then collecting data about that transmissivity and leakage to design a mitigation system. So, first of all, we used the data to come up with a site-specific screening level, which now is 130 micrograms per cubic meter, for like a generic non-residential for TCE. Using high volume sampling, we established a site-specific screening level of 3,000 micrograms per cubic meter because we're getting better attenuation at this building. And then designed a mitigation system to address that area. So it's kind of hard to see here, but we have these black points within this mitigation area. That's where we have an extraction point. We have 12 points which are connected to 5 fans mounted inside this courtyard. And if you can discern the points, you can see that there's kind of a tighter density of them on the west side of this courtyard and a lower density on the east side. Well, that's because we have a leakier slab on this side, a more confident slab on this side, so we can get better vacuum propagation on this side compared to this side. So once we did this testing, installed this mitigation system, did some performance monitoring, our TCE concentrations in indoor air are now below 2 micrograms per cubic meter. We're getting good vacuum across our target mitigation area. We can also look at the mass capture rate by that system, and you can also think about what was coming into that building to generate the indoor air concentrations pre-mitigation. So that flux that's captured by the system is comparable to what was coming into the building beforehand. So it's a good sign that we are effectively capturing what used to be coming into the building. So our mitigation system is doing what we wanted to do. It's performing as designed. So this is our kind of vacuum field that we're getting from that. You can see that that kind of matches up pretty well with the target mitigation area, previous slides. Okay. So I'm really good on time. That's where I wanted to be. I know I breezed through a lot. So if there are any questions, I'd be happy to take them now.
Mitigation process take?
How long does the mitigation process take? That's a good question. So, I mean, typically, like the high volume sampling was about, a week or 2 in the field. Then there's maybe a couple months of digesting the data, designing the system. Putting in the system was probably about 2 weeks. We also have to sort of get a mitigation contractor going and get quotes from them and all that fun administrative stuff as well. So, it's typically, probably a few months process from going out to get the data to design the system to having an installed system mitigating the building. There's a lot of other variable that can come into play too with the, property owner signing off on the system and all this.
Yeah, I wonder if you ever have concerns from neighboring properties when you do a mitigation at a certain property, which means you're not allowing that subsurface contamination to come into your property. But it's gonna wanna go somewhere.
Right.
So it's gonna travel underground and it could come up at your neighbor's house and now they have a problem.
Right. So a few different responses to that. So first of all, yeah, I mean, we would be like from the beginning looking at that vapor source, looking at that investigation area, and thinking about, is there a vapor intrusion risk at, other properties around our source area? For the mitigation system itself, the vapors that we're capturing should be going up above the building and then kind of mixing and diluting with the outdoor air. And there's guidance about like where that extraction point needs to be, that discharge point, so that you're giving it enough room to mix with the indoor air and not like having those vapors just go up and then get sucked into somebody's window. So it needs to be like above the roof line, it needs to be a certain distance away from other buildings, it needs to be a certain distance away from doors, windows, like entry points for heating and cooling systems. The other thing is we've definitely had complaints from neighbors after we put in a mitigation system about the noise of the fans that we put in. So it's, it's not just the sort of technical nuts and bolts side of things, but, there's other considerations that come into play. So for that, we kind of suspected that noise might be an issue, so we were ready to go and put in some mufflers on those discharge stacks, and that knocked down the noise a lot. But that is something I'm kind of going through with a property owner right now, where she's not happy with the noise level of the fan on her house, correcting the vapor intrusion issue for her property. But, that's not the only consideration that people have. I will say too, there are buildings where, the source is so significant that we actually need to treat the vapor before it comes out of the stack. So we have like carbon drums that are, the VOCs are sorbing onto the carbon instead of going out into the outdoor air. And that way we can, it's like different permit exemptions for these mitigation systems on the air side, so we don't have to, get an air permit to address this sort of local health concern.
Thank you.
Yeah.
Are there any questions online? You got it.
So I have a couple questions. One was on your previous slide, I think here, or the site schematic showing like the sewer lines, and I noticed, were you doing sampling along those sewer lines, and was that like one of the main considerations for how you were evaluating the site, or do you see preferential flow pathways? I know this was a specific example.
Yeah, that's a good question. We did not specifically look at that. I know there's a part of the building that's almost like a half basement. There was a sump in there, so we did look to see like whether that sump was a preferential pathway.
Yeah.
We didn't look directly at the sewer lines. I'm trying to remember why. I don't remember offhand why that was. If that evaluation had already been done by a different consultant, so we kind of took this over from the incumbent. So maybe that had already been evaluated and found not to be a problem.
I guess also just to follow up too, at least I've seen it at some of the sites I've worked at where the sewer lines, they are a preferential flow pathway, and then they'll get into neighborhoods. Are there guidelines for once the gas is, I don't know, across the street or something in the sewer lines, is that something that you guys look at, in terms of you can't have the exceedance of the sewer concentration being at a certain level coming off of a site.
Yeah, well, I'll say a couple of things. Yes, we do look into that. I'm actually gonna be going in tomorrow and getting water samples and vapor samples from the, like a creek drain. I will say, like, as, you know, technical community, I think we're still trying to get our arms around preferential pathways, conduit VI, whatever people want to call it. I know Michigan doesn't, I don't think they have like real specific guidance on that. I mean, they want you to consider it and investigate it, but I don't think they have, like, this is your sewer vapor screening level that you're comparing to. I think Wisconsin DNR is a little more down the road on that. But it's kind of the new hot topic in BI that the industry is still trying to get their arms around.
Okay. Yeah, I've seen some things where they take the indoor air levels and then they just make that the sewer levels because it's a direct, could be considered direct contact.
Yeah.
Yeah,
I think like what Wisconsin does, and I'm more in favor of this approach, is maybe different screening levels for like the lateral, like between the house and the main, than what's in the main itself. Because I think, you know, the main, I think I've seen like 0.1 or 0.03 attenuation factors, but then having an attenuation factor of 1, so like no attenuation from what's in the lateral of that house to or the service line to indoor air.
okay. And then my other question too, this was a while back, but I think it was a Dawson McGallery 2009 study. Toluene was the most common compound that you would find inside of a house, which I always thought would be benzene, which is farther down, or the third one there. I don't know. Do you have any thoughts on that, or do you know why you see toluene more often?
Yeah, that's a good question. I do feel like in my experience, I've seen benzene more than toluene and xylene.
I mean, that's what we've seen in our field sample here, clear too.
Yeah. I also think, I mean, some of that might be too that like the screen level for benzene is lower than toluene and xylene, so I care more if there's 2 micrograms per cubic meter benzene versus 2 micrograms per cubic meter xylene. I guess not the right way to say that, but yeah, and you know, looking at these numbers, I don't know that I would, you know, assign a material difference between like the rates of detection between those two. They're, you know, everything like ethyl benzene up on this chart, I feel like is probably comparable, and you know, probably similar sources from those are coming from.
Thanks.
Yeah. Any questions online?
Nothing in the chat.
Okay. Anybody else?
All right, thank you very much.
Thank you.